Tutorial sheet for question 5. A super Het receiver for a radar is tuned to a signal frequency of 2.8 GHz and has a local oscillator frequency of 2.86 GHz. A second identical receiver located nearby has its local oscillator set at the image frequency of the first receiver and interference results. So we've got 3 questions to answer on this question. First of which is, what is the IF of the first receiver? So let's consider what the scenario is, and we've got 2 receivers essentially. We've got receiver 1 and receiver 2. So these are just antennas, and the first receiver is tuned to a signal, so an incoming signal into here with an RF frequency of 2.8 gigahertz, and it has a local oscillator which is equal to 2.86 gigahertz. So that's what we're told about the first receiver. And then there's a second receiver which is identical to the first receiver, and that is set with a local oscillator initially, so that would be FLO2, which is set at the image frequency of the first receiver. So that's the information we're given, and interference occurs, and so this is system 2, and what we're assuming here is that the local oscillator in this system is actually transferring some energy out of this antenna. So some of the energy from the local oscillator is leaking out of this antenna and causing interference with this system here. So first of all, we need to calculate what is the IF of the first system. So we have a local oscillator of 2.86 and an RF frequency of 2.8. So IF is equal to the difference between these two, which is 60 megahertz. And because both systems are identical, the IF for both of these are exactly the same. It's the same design. So IF1 is equal to IF2, which both equal to 60 megahertz, because they are identical receivers. And then part B says, to what signal frequency is the second receiver tuned? So in other words, at the minute the local oscillator, the second local oscillator, is set to the image frequency. And what we need to know is what is the local is the RF frequency that the second system is tuned to. So first of all, we've got to work out what the image frequency of the first system is. So the image frequency in this case is twice the IF above the RF frequency. So the F image is equal to FRF plus 2 FIF, which is equal to 2.92 gigahertz. So that's what the local oscillator is set to. So the RF frequency, which is now going to be the difference between the local oscillator and here, has got to be, so the IF has still got to be 60 megahertz, so that F image 1 minus FRF2 still has to be 60 megahertz, because they are identical receivers. So FRF2 is 2.86 gigahertz. So that's the first 2 parts of the question. Last part C, says if the receivers were to be redesigned, what should be the minimum IF to prevent interference problems in the 2.8 to 3 gigahertz radar band? So in other words, we don't have a set frequency that we're aiming at. We've got a band of frequencies which are going from 2.8 to 3 gigahertz. So we need to first of all write down some equations that describe the two systems. So first of all, we've got something that we've had before. So F image, frequency of the image, is the first frequency plus 2f IF, which is from here. So that's equation 1. We also have that the local oscillator 2 minus FRF2 has got to be equal to the FIF, because they've got to be and also that they are the same, because FIF1 is equal to FIF2. So we've got, if we rearrange, we've also got as well that the local oscillator 2 is equal to the image frequency of 1. That's when interference will occur. So we can rewrite this equation as F image 1 minus F RF2 is got to be equal to FIF, just by rearranging this equation. So we've got now two useful equations, 1 and 2. If we rearrange, substitute equation 2 into equation 1 and get rid of F image, we get that F RF1 plus 2 FIF has got to be equal to FRF2 plus FIF. So our FIF has got to be equal to FRF2 minus FRF1. And what we're trying to do is maximize this, because FRF could be anywhere between 2.8 to 3 gigahertz. And so we want to maximize this. So the maximum that this could be is going to be 3 gigahertz, and the minimum is 2.8 gigahertz. So if you do the subtraction of the maximum and the minimum, that gives you your final answer, which is 3 take away 2.8, which is equal to 0.2 gigahertz or 200 megahertz.